Hello everyone, welcome to Analysis 1 video 16, and this is the video where we are going to define what it means for a sequence to converge. To start with, I thought I'd share with you a way that I like to picture what a sequence looks like, because I find it really helpful to have these sort of diagrammatic representations of sequences that I can use to get the informal aspect to go alongside the formal. And what you'll find as we go through this section and look at various proofs relating to sequences and so on, is that I want to try to stress the informal intuition and the formal careful proof. And for me, both are really important. You can't just have one or the other. And so the interesting bit comes in getting from one to the other. If I've got a formal proof that someone shows me, how do I think about it intuitively? If I've got an intuitive idea of why a result's true, how do I write down a careful formal proof? And I want to try to draw those things out as we're going through this. So how do I visualize the sequence? Well, there are lots of ways we might do it. One way I like to do it is sort of think of it kind of on axes. And I put the first term at 1, A1, and the second term at 2, A2, and the third term at 3, A3, and so on. So I've got a diagram here. Some of these I'm going to sketch by hand later on, but I thought I'd do a few of them on the computer, which is a little bit more accurate than me, where we've got particular examples of sequences. So the sequence where the nth term is -1 to the n, I've plotted here, so I've got a horizontal axis that kind of starts at 0 and goes on up, and then I've got positive and negative y-axes, vertical axes showing. And then I've plotted 1, -1, 2, 1, 3, -1, 4, 1, and so on. So what we end up with is a row of dots at -1 and a row of dots at 1 vertically, vertically at 1 and at -1. And we can sort of see that the sequence is then oscillating. Why have I drawn them as isolated dots rather than joining them up? Well, there is no notion of what this sequence means. It doesn't mean anything at all between 1 and 2 or between 2 and 3 or whatever on the horizontal axis. So it wouldn't make sense to join them up, but it makes perfect sense to draw the isolated points. And I think this is a useful way of seeing what's going on. So if I just keep going with the examples that I had from the last video, we had a sequence where an is 0 if n is prime, and it's 1 + 1 over n for other values of n. So this kind of defined via these two cases. This one looks a bit more complicated, but we've got, when I look at the way I've drawn it here, it sort of stands out that we've got 0 at the points 2, 3, 5, and 7 along the horizontal axis. Those primes, we know the sequence is 0. And then away from that, so at 1 we've got 2, at 4 we've got 5/4, at 6 we've got 1 plus a sixth, so 7/6, and so on. And so there's sort of, I guess, kind of somehow it looks like they're kind of tending down towards 1 there, but also there are these values at 0, and the next point would be at 11, 0. So there's something a little bit complicated going on there. Another example we had was an is sin n over 2n + 1, and I just end up with a bunch of points that are pretty close to 0, actually, but just slightly oscillating above and below the horizontal axis there. And then I have one more example, which was an is n, and then we end up with these points lying on the straight line, y = x, unsurprisingly, but just at these integer points. So when I'm thinking about sequences, I like to visualize them using this sort of graphing technique. When I'm thinking about a general sequence, I want to try to have in mind the variety of things that might happen. It's quite tempting to draw pictures of sequences that are very special type of sequences, and I want to try to avoid doing that. So when I'm drawing examples later on, I will try to draw quite generic examples, and you can look at the ones I draw and try to think, well, what's generic about those? So how are we going to define convergence? I'm going to draw a picture, and then I'm going to try to tease out from the picture what the formal definition is. And I'm going to do that on my piece of paper, and then I will put the formal definition on the slide afterwards. But I hope that the picture will be helpful for at least some of you. Okay, I'm going to draw myself a set of axes like the ones on the examples that we just saw. So a horizontal axis for non-negative values, and then a vertical axis that can take positive and negative values. And I'm going to draw on some points of a sequence, just any old sequence. So I'm not drawing this very carefully, I'm just putting some dots. There are some positive values, There are some negative values. The sequence goes up, it goes down, maybe stays the same for a bit. It kind of wobbles around doing its thing. And I want to know, what does it mean to say that this sequence tends to a limit? Let's draw on where we think this limit might be. This is a bit hard to tell from a rather informal sketch like this, but I'm just going to put a horizontal line. Maybe this is where the limit is. This is just some horizontal line a little way above the horizontal axis with height L above the axis, L being our proposed limit. And then our evil opponent comes along, and our evil opponent challenges us with a small positive epsilon. So maybe they challenge us to epsilon is 0.1. What does that challenge mean? It means that we draw in the lines, horizontal lines at height L plus epsilon and L minus epsilon. And I'm doing these as red, but I also do them as dashed lines, make it clearly distinct from the blue line at the limit L. So we draw on these lines at L plus epsilon and L minus epsilon. And our evil opponent challenging us to epsilon is 0.1 means that we draw these lines at L plus 0.1, L minus 0.1, or L plus epsilon, L minus epsilon, and say, is there a point on the horizontal axis beyond which all of the terms of the sequence lie within epsilon of the limit? And on the basis of the evidence here, which is rather flimsy because I've only drawn finitely many terms of the infinitely many terms in the sequence, if I put a vertical line at this point n, so n is where it crosses the horizontal axis, beyond that, so beyond this point, to the right of it, I mean, all terms lie within epsilon of L. So after the point n on the horizontal axis, to the right of that, all of the terms of the sequence lie in this strip between L minus epsilon and L plus epsilon. And then our evil opponent says, well, actually, 0.1 was a really large value epsilon. I challenge you to 0.0001. And we say, well, that's okay. We'll just draw a new picture where our red dashed lines are a little bit closer to L. They're at 0. Whatever it was, the new epsilon from L. And maybe we have to look further to the right in our sequence. But as long as there is some point beyond which all of the terms are eventually that close to the limit, we're all good. So what does it mean for our sequence to converge to this limit L? It means that whatever positive epsilon our evil opponent chooses, there is some point, n, beyond which all of the terms of the sequence are that close to the limit, at least that close to the limit. So from some point on, all of the terms of the sequence are within 0.1 of the limit. From some point on, which might be much further down the sequence, all terms of the sequence are within 0.0001 of the limit, and so on. Which sort of seems plausible, hopefully, as a definition for convergence. Eventually, you can make the sequence as close as you like to the limit. We don't say that you have to equal the limit, you don't have to hit the value or anything, but you can be as close as you want, as long as you go far enough down the sequence. How do we make that precise? Let's give this a go. So I'm going to do this drawing handwriting under my diagram, and then I will put a formal definition up on the slide in a moment, as I promised. So what we're saying is that we're trying to make the terms of our sequence, so that's the terms of the sequence within epsilon of the limit. And the way that we can write that in symbols is to say that the absolute value of an minus L, the modulus of an minus L, is strictly less than epsilon. If you need to just kind of pause to unpick what that's saying, I mean, what it's saying is that an is between L minus epsilon and L plus epsilon, but it's much more convenient in this form using the modulus sign. So the absolute value of an minus L is less than epsilon. And we want to know that as long as we're far enough along, that will be true. So we want to know that there's some capital N such that for all little n greater than or equal to n, it's true that the absolute value of an minus L is strictly less than epsilon. And we want to know that there is an n so that this is true. So we want to know that there exists a natural number n such that, I'm just going to put ST for such that this is true. So our evil opponent has given us their epsilon, and we want to know that there exists a natural number n, some point on the horizontal axis beyond which, such that for all n greater than or equal to n, an is really close to the limit L. How do we factor in that whatever epsilon our evil opponent chooses? Well, at the beginning of this statement, we have a for all epsilon greater than 0. So our definition, an tends to L as n tends to infinity, if for all epsilon greater than 0, there exists an capital N in the natural numbers such that for all little n greater than or equal to capital N, the absolute value of an minus L is less than epsilon. And I hope that you can kind of see how that relates to the picture I have attempted to draw. I hope that you can sort of visualize what this definition is saying and why this makes sense with our interpretation of convergence. Let me put this on the slide. So, definition, let an be a real sequence and let L be a real number. We say that an, the sequence an, converges to L as n tends to infinity if, for all epsilon greater than 0, there exists a natural number n such that, for all little n greater than or equal to capital N, the absolute value of an minus L is less than epsilon. And in that case, in the case when this is true, we write that an tends to L as n tends to infinity. So it tends to, written using this right pointing arrow, I would read it as tends to. We write an tends to L as n tends to infinity, and we say that L is the limit of the sequence an. And I'm trying to get into the habit of saying sequence an, meaning it's got brackets around it. If I just say an is a term, I might forget, but I'm going to try to do that. This is quite an intimidating definition. If you are looking at this and thinking, oh my goodness, please don't panic. You will get used to it. You will get comfortable working with it. It just takes a bit of time because it's new. I know it looks a bit, oh my goodness. Let's make a few comments about this. So I might also say that the sequence tends to L, converges to L, tends to L, same thing, as n tends to infinity. And notation, we might write that lim with n tends to infinity written underneath lim of an is equal to L. So that's another way of saying the sequence an tends to L, lim as n tends to infinity of an is equal to L. I advise extreme caution using that notation because people have a habit of writing that down and not carefully checking whether the limit exists in the first place, which is an issue, and I'll try to touch on that when it crops up later on. Tends to, converges to, same thing. I think sometimes people have ideas about tends to might mean gets closer and closer but doesn't get it, doesn't reach the value or something. I don't care whether the sequence takes the value L or not. It makes no difference at all for convergence. Our definition doesn't comment on that. Our definition also doesn't say each term has to be closer to the limit than the previous one. Some sequences that's true, but not all of them. The one I drew was kind of more complicated than that. So the sequence might be really close to L and then move away a little bit, as long as it meets the definition that from some point on, all the terms are close enough to the limit, for all possible close enough somehow. Our choice of capital N can depend on epsilon, and it almost always will depend on epsilon. And I tried to capture that with this sort of story about the evil opponent earlier on. Our evil opponent challenges us to 0.1, and we might choose our capital N in light of that. If our evil opponent comes back and says, well, I challenge you to 0.001, we're allowed to choose a new capital N. How is that captured in the statement? Well, slogan, the order of the quantifiers matters. So the definition says, for all positive epsilon, there exists a capital N. And that means your evil opponent specifies your epsilon. We don't get to choose it. It's for all epsilon. Our evil opponent can pick any positive epsilon. Then there exists an N. So the story says evil opponent picks their epsilon, then we choose our N. If the definition had said there exists an N such that for all epsilon, positive epsilon, that would mean we have to choose our N and put our cards on the table, and then our evil opponent can choose their epsilon, and that's something completely different. So it's really important when you're writing down these kind of statements that the quantifiers come in the right order to say what you want them to say. What could we change in our definition? Well, we could change n, little n greater than or equal to capital N. We could change that to little n strictly greater than capital N. That makes no difference to the definition. We could replace modulus of an minus L is strictly less than epsilon by modulus of an minus L is less than or equal to epsilon. Makes no difference to the definition. A really useful thing for you to do at this point would be to pause the video and think about how come that doesn't change the definition. But it is really important that we have for all epsilon positive, not for all epsilon greater than or equal to 0. So some of the inequalities, it really matters. Some of them it doesn't. And if you can think through which ones it does and which one it doesn't, that means you kind of have a really good understanding of what's going on. In the definition, I said the limit. Maybe there could be more than one limit. In fact, it turns out that if there is a limit, then it's unique, and that will be a theorem that we will prove later on. So that's not supposed to be something that you can see right away now. We will prove that carefully together on a video at some point soon. So I've talked about tending to a particular limit, convergence to a limit. Now the definition, we say that if we've got a real sequence AN, we say that the sequence AN converges or is convergent if there is an L in the real numbers such that AN tends to L as n tends to infinity. So the first definition with the epsilon and stuff was converging to a specific limit L. And then what does it mean for a real sequence to converge? It just means it converges to some limit. There is an L such that the sequence converges to that L. And on a related note, we can then say what it means for a sequence to diverge. So if the sequence AN doesn't converge, then we say that it diverges or is divergent. So diverges, opposite of converges. We're going to move on in a moment and keep developing the theory, but I think now would be a really good time for you to pause the video and, without looking at your notes or the video or whatever, see, can you reconstruct that formal definition of the convergence of a sequence? If you watched the video and you thought, gosh, this is a bit confusing, then taking a bit of time to go back and revisit it would be really helpful. If you watched the video and thought, oh yes, this all makes perfect sense, it's really helpful to go and kind of probe how much of that has sunk in. I know from my own experience, I can watch something, I can listen to somebody talk, I can watch a video, oh yeah, that will make sense. But then 5 minutes later, if I try to reconstruct it, it turns out it hasn't really sunk in. I've sort of nodded my head and go, yeah, okay, I get that. Actually, I haven't quite got it. So I really encourage you to pause now and see, can you draw the diagram, the informal picture? Can you reconstruct the story about the evil opponent? Can you write down the formal definition? Not just remembering it verbatim, not just remembering because you've remembered the symbols, but understanding what it means, telling yourself the story of why this is our definition of convergence, because the rest of this course is kind of going to build on this definition. So this is a really good one to get your head around. Okay, hopefully you've just consolidated your understanding of convergence. You've gone back over that. Let's keep going. So one thing I want to comment on is that our definition of convergence, whether or not a sequence converges, shouldn't really depend on the first 100 terms of the sequence, or the first million terms of the sequence, or the first squillion terms of the sequence. Because all that matters is what happens eventually far enough down the sequence. Maybe the sequence goes wild for 1,000,000 terms, but then it does something quite sensible. And the wildness for the first 1,000,000 terms shouldn't have any effect on whether or not the sequence converges. And I want to make that precise. And to do that, we're going to have a result, but first we're going to have a definition. And this is a definition of a tail of a sequence. So if we let us AN be a sequence, brackets AN be a sequence, a tail of the sequence AN is a sequence BN, where for some natural number K, we have the BN is equal to A n plus K for n greater than or equal to 1. Putting that another way, the sequence Bn is the sequence you get by deleting the first k terms of An. If you look at the subscripts, what I'm doing here is just chopping off the first k terms from the sequence and kind of renumbering so that our new sequence B1 is A k plus 1, B2 is A k plus 2, and so on. So a tail is just what you get by chopping off the first k terms for some k. And that sort of pins down this idea of for the first 100 terms or the first 1,000,000 terms or whatever, we can lose those. We can do that by considering a tail. So now let's look at our lemma. This is lemma 23, and this is called the tails lemma. So if you want to refer it later on, you can say by the tails lemma. And it says two things. It says let AN be a sequence. The first part says if the sequence AN converges to a limit L, then every tail of the sequence AN also converges and to the same limit L. So it sort of doesn't matter where we start our sequence. We can chop off the first few terms. The sequence will still converge and to the same limit. And the second part says, if a tail, Bn, which is, say, the sequence A, n plus k, if a tail of the sequence An converges, then the sequence An converges. So if you can chop off the first million terms and have a convergent sequence, then the whole sequence converges. So hopefully you can see how the tails lemma makes precise this idea that the behaviour of the first finitely many terms has no effect on convergence. That's the kind of executive summary. And we're going to have a go at proving this, and this is going to be our first opportunity to work with our definition of convergence. So I will prove the convergence of some sequences using the definition, but there will be rather more proofs of results using that definition, and I'd like you to think of all of them as kind of worked examples of how can we work with this formal definition of convergence, and we'll do that with the tails lemma. So the first part, we're going to assume that our sequence converges and take a tail. So let's take our tail first. It doesn't matter which order we do this. So let's take a tail, say the sequence Bn, which is the sequence A n plus k of the sequence An. And let's assume that the sequence An converges, say, to L. Let's give the limit a name. And what we want to do is to show that the sequence Bn, this tail, converges to the same limit L. So what we need to do is prove that it satisfies this definition that we've just seen, that for all positive epsilon there exists a capital N such that blah blah. How are we going to do that? Well, the first thing I want to do is notice we're trying to prove a statement to the form for all positive epsilon such and such is true. How do we do that? We pick an arbitrary positive epsilon and show that it works for that. And I don't mean we pick epsilon as 0.1 and show it works for that, because that's not general. I mean we pick an arbitrary one in the sense that we just fix a specific value that we work with, but we don't say what it is. So let's fix some positive epsilon. I'm not saying what it is, it's just a fixed value. And what we want to do is work with that one, show that for this one there is a capital N. And because this was arbitrary, that means that we'll have proved the result for all positive epsilon. Why am I stressing that? Because we are going to prove many results of the form for all epsilon greater than 0, such and such is true. And a go-to strategy would be the first line is let's just fix a value and then work with that. At some point we need to use the fact that our sequence AN converges. So let's deploy the definition of the sequence AN converging to L with this particular epsilon. So since AN tends to L as n tends to infinity, there exists a capital N in the natural numbers such that, I'm going to keep writing ST for such that, I hope you're happy with that, if little n is greater than or equal to capital N, then the absolute value of AN minus L is less than epsilon. Why have I written if n is greater than or equal to n then, rather than for all n greater than or equal to n, such and such is true? I find the logic easier to work with in this way. I stated it the other way in the results because it's easier to negate the statement with the for all. So they're equivalent, they say the same thing. Pause and check if you need to think about why they say the same thing. So we know that there's some n such that beyond that point, all of the ANs are really close to L. And that means that the BNs must also be really close to L, because the BNs are A n plus Ks. So all we have to do is kind of write that down carefully. So now if little n is greater than or equal to capital N, then n plus k is certainly greater than or equal to capital N, because k is a natural number, it's positive. So we know that the absolute value of a n plus k minus L is less than epsilon. We know that if your subscript is past n, then a subscript is close to L. that's what I'm applying here, that is the absolute value of Bn minus L is less than epsilon, because remember that's how Bn was defined. It's an plus k. And this is exactly what we wanted. We wanted to know that there is an n so that past that point, all of the Bn's are within epsilon of L. That's exactly what we've proved. So this shows that the sequence Bn converges and Bn tends to L as n tends to infinity. And that proves the first part. Now let's see the second part. So this time we assume that a tail converges. So let's assume that the sequence Bn, which is the sequence an plus k, converges. And let's say to L again. And now what we want to do is show that the sequence an converges. And of course we sort of know it's going to tend to L also. So let's do a similar kind of strategy. Let's fix epsilon greater than 0. Our evil opponent has specified their epsilon. And now we need to show that past some point, all of the ANs are really close to L. And that must be true because all of the AN plus Ks are really close to L. So intuitively, I think this result is quite clear. We just have to write it down carefully. So let's apply the definition of the convergence of Bn with this epsilon. So then there exists an capital N in the natural numbers such that if n is greater than or equal to capital N, then the modulus of Bn minus L is less than epsilon. That is, the modulus of an plus k minus L is less than epsilon. And now, if little n is greater than or equal to capital N plus k, then n is equal to little m plus k, where m is greater than or equal to n. And so the absolute value of a subscript n minus L is the absolute value of m plus k minus L is less than epsilon. M is far enough down the sequence that m plus k is close to L, and that's the same as saying that an is close to L. So this proves that the sequence an converges, and in fact also an tends to L as n tends to infinity. And that proves part 2. So you might be wondering why I switched from n to m. Well, this is just a dummy variable in the jargon. This is just saying if n is large enough, then something's true. Well, we could call this little n m instead. It doesn't matter. So hopefully you can see how the formalism of this argument relates to the intuition that says these are really the same sequences. They've got the same terms in the region that we're talking about. Good. Where next? Let's prove that some actual sequences converge. So let's have an example. Let's claim that 1 over n tends to 0 as n tends to infinity. So this isn't a numbered result in the notes. This is just a kind of worked example for you. So how are we going to prove this? Well, we go back to the definition. Always, we go back to the definition. We need to show that whatever positive epsilon our opponent picks, we can show that as long as you go far enough down the sequence, all of the terms are going to be within epsilon of 0. Is that true for the sequence 1 over n? It absolutely is. You can see why that's true. We sort of talked about it, in fact, in an example in the previous video. I just want to write it down carefully. So let's fix epsilon greater than 0. And then there exists a capital N in the natural numbers such that 1 over n is less than epsilon. That is by the Archimedean property. If you remember that, suddenly the Archimedean property is going to prove very useful. And now, if little n is greater than or equal to capital N, then 0 is less than 1 over little n, is less than or equal to 1 over capital N, is strictly less than epsilon. And so the difference in absolute value between 1 over n and 0, that's what we're interested in here, which is just 1 over n, right? That's less than epsilon. And so 1 over n tends to 0 as n tends to infinity. That was not the most complicated example, but it is a really useful example. And the fact that 1 over n tends to 0 as n tends to infinity will be important to us later on. Let's do a slightly more complicated example. So, claim I'm going to let an be 1 plus minus 1 to the n times 1 over root n for n greater than or equal to 1. What happens to this as n tends to infinity? You might want to pause the video and think for a moment. We are doing 1 plus or minus something that's getting pretty small. So intuitively, it seems plausible that an tends to 1 as n tends to infinity, and that's what we're going to prove. So how we're going to do this, as usual, we're going to take an epsilon greater than 0. We're going to fix an arbitrary positive value, and we're going to work with that. And this is the kind of argument that I can't just write forwards straight away. I need to stop and do some doodling first. If you look at the slides, you won't find any doodling, and it will be a bit mysterious. That's because I'm going to talk through it in the video. If you look in the notes, I have tried to capture the doodling in grey in the notes. So let me take a coloured pen for doodling. So what we want is an n such that if little n is greater than or equal to capital N, then the modulus of an, which is 1 plus minus 1 to the n, 1 over root n, minus 1, the modulus of an minus 1 is less than epsilon. That's what we're aiming for. And we're going to do this by saying take the following value of n, but we have to work out what is a good value of capital N. And to do that, we need to mess around with some inequalities for a bit, being careful with the logic. And we're sort of working backwards, but not, because we're being careful about the logic here. That's why I'm doing it unofficially in a coloured pen. We'll do it properly in forward direction in black pen once we've worked out what we're doing. So that is, by which I mean this inequality is the same thing as saying, so the ones cancel, 1 minus 1 cancel, and when I take the modular signs, this minus 1 to the n is going to disappear. So what we're interested in here is that 1 over root n is less than epsilon. That is, n is greater than 1 over epsilon squared, this little n. That's what we're kind of aiming for here. So if we could pick a capital N, so that for all little n greater than or equal to capital N, we had little n is greater than 1 over epsilon squared, then by running through the inequalities in the correct direction, we'd be in business. Is there such a capital N? Sure, we just pick an integer bigger than 1 over epsilon squared. So back to black. How are we going to do this carefully? I'm going to let capital N be 1 plus the ceiling function of 1 over epsilon squared. So this isn't a modular sign, this is modular signs but with little horizontal corners on the top. So this is supposed to denote the ceiling, and this means the smallest integer greater than or equal to the thing inside the ceiling brackets. So the ceiling of x is the smallest integer greater than or equal to x. Putting that another way, informally, if it's an integer, if x is an integer, then the ceiling is just x itself. Otherwise, you round up to the next integer. So the ceiling of 1 over epsilon squared is an integer greater than or equal to 1 over epsilon squared, and then I'm just adding 1 for safety. And then if little n is greater than or equal to capital N, then I know what to write by looking at what I did informally in blue previously. So little n is greater than 1 over epsilon squared. I think I'm just going to move this up so that I'm still on the screen for you. So 1 over root n is less than epsilon, just rearranging the inequalities. So the absolute value of 1 plus minus 1 to the n, 1 over root n, minus 1, is less than epsilon. So the absolute value of an minus 1 is less than epsilon. So we've showed that whatever positive epsilon we start with, there is a capital N, which we defined in terms of epsilon, such that if little n is greater than or equal to capital N, past that point, all of the terms of the sequence are within epsilon of 1. The modulus of an minus 1 is less than epsilon. And that shows that an tends to 1 as n tends to infinity. So I hope that that's sort of helping you to make sense of the definition. I hope that's also giving you an idea of how do you go about constructing these things. So if I were writing this up, I would hide the bit in blue, which was my private doodling on the back of an envelope. I'd say, let n be the following thing, and everybody would think, hang on, where did that rabbit come from out of that hat? But the answer is because I did some private doodling, and it works out nicely. With all of these parts of the course, I'm going to do some examples in the lecture videos, but I don't have time to do lots and lots. If you have a look at Hilary Priestley's notes on the Canvas page, you will find there are some additional examples which might be useful for you. One more example now. Let's think about the sequence an, which is n cos n cubed plus 1 all over 5n squared plus 1. For n greater than or equal to 1. Why have I chosen the sequence? Because it's not very nice. It's not going to be super nice, proving that it converges from the definition. We will see other potentially nicer strategies in later videos, but I want to demonstrate now a couple of tips for how, even with some kind of quite disgusting sequence like this, we can handle it quite well. What happens to this sequence as n tends to infinity? Well, maybe pause the video and go to Desmos or MATLAB or your favourite graphing thing, have a look at what this thing looks like. Can you get some intuition for what happens? My intuition is the top, well, cos is bounded by 1. Well, this is cos of n cubed plus 1, which is revolting. Cos is only ever between -1 and 1. So the numerator here is kind of between minus n and n, whereas the bottom, 5n squared, the n squared there is going to be much more important than the n in the long run. So I think that an tends to 0 as n tends to infinity. That's what we're going to try to prove. And hopefully that seems like a plausible claim for you. So how are we going to prove this? Well, you know the drill. We take epsilon greater than 0, and let me grab another colour and informally try to think about how are we going to come up with our n. So we want n such that if little n is greater than or equal to capital N, then the absolute value of an, I'm going to write it out directly, so n cos n cubed plus 1 over 5n squared plus 1, we want to know the absolute value of this minus 0, so I'll just close the absolute value signs, is less than epsilon. Yuck. I cannot possibly try to somehow solve this inequality to find n in terms of epsilon, but I don't need to. So the key thing I want to stress in this example is that your philosophy should be, how can I make my life easier? What can I do to simplify things without throwing away anything important so that my life is easier? We need to make sure this inequality is true. We don't care about the smallest possible n that will work or anything. And we might note that cos of n cubed plus 1 in absolute value is at most 1. So it's enough to have that the absolute value of n over 5n squared plus 1 is less than epsilon. To try to clarify the logic here, if we could find a capital N, so that whenever little n is greater than or equal to capital N, we have the absolute value of n over 5n squared plus 1 is less than epsilon, then the absolute value of an, the thing we're interested in, is less than or equal to that, so it's also less than epsilon. And, oh look, I've just got rid of the horrible, disgusting cos term. And buoyed by my success there, I'm thinking we could do something similar. The 5n squared plus 1, we could throw away the plus 1 as well. So in fact, it's going to be enough to have the absolute value of n over 5n squared being less than epsilon, because n over 5n squared plus 1 is less than n over 5n squared. And n over 5n squared is good because it's 1 over 5n. So 1 over 5n less than epsilon. So this says if we could make n bigger than 1 over 5 epsilon, we'd be good shape. So now I'm kind of getting an idea of what to pick for my capital N. So I think I'm ready to grab my black pen again. So let me just slide this up. So I'm going to let n be the ceiling of 1 over epsilon plus 1. Because if little n is greater than or equal to capital N, then certainly little n is greater than 1 over 5 epsilon. Why did I go with n being the ceiling of 1 over epsilon rather than 1 over 5 epsilon? Well, it doesn't matter. I don't care. I can make n much larger if I want to. I'm not trying to be efficient. I just need a value that works. And this way I didn't have to think about it too much. I could just see that it would work. So n is greater than 1 over 5 epsilon. And now I do the sort of same strategy as before, just kind of going through the coloured bit, but backwards. So that tells us that n over 5n squared, I could put absolute value signs around it, doesn't matter, is less than epsilon. So the absolute value of n over 5n squared plus 1 is less than epsilon, because that's less than it. So the absolute value of n cos of n cubed plus 1 over 5n squared plus 1 is less than epsilon. And that tells us that an tends to 0 as n tends to infinity. Trying to make sure I stay on the screen for you there. So I could have written this last bit a tiny bit more concisely. I didn't need to do these in separate steps. I could have just used the inequalities. I just wanted to try to relate what we were doing here to what we'd done with the coloured part informally previously. I hope this is helping you get some ideas for this philosophy of use inequalities, make your life easier. Everything you write down has to be true. It doesn't necessarily have to be the best possible value of n. And there's a question on sheet 3 that invites you to get some experience of this. We are nearly at the end of this long video. Let me just finish with some top tips for you. So I've just stressed we don't need the smallest possible n. Do make your life easier. Make sure your inequalities are in the right direction. Think about the logic. Make sure that the logic goes the way you want it to. It's very easy to end up going backwards. And I hope that the examples I've just done will help you to see the kind of thing that I mean. The definition says capital N's a natural number. Actually, we don't really care whether it's a natural number, because if we've got a value that works, we could just pick a natural number that's larger than it. So if I'm a bit cavalier and don't always say n is a natural number, that's because I sort of don't care. It doesn't really matter. We think of epsilon as a small positive real number, but our opponent is entitled to choose epsilon as 1,000,000 if they like. But if our evil opponent chooses 1,000,000 and we already know it works for 0.1, then we win, right? Because anything that works for 0.1 will work for 1,000,000 as well. Any value of n that works for 0.1 will work for 1,000,000. So if we have an n that works for some particular value of epsilon, it works for larger values of epsilon. Why am I mentioning that? Because sometimes it's convenient to say, take epsilon between 0 and 1. Maybe there's some reason why that simplifies life a little bit. So we can absolutely do that. We should just mention one line why. If we do it for epsilon between 0 and 1, that's enough. Final top tip for now. I was doing everything here using modulus signs and inequalities, and I really recommend getting comfortable doing that too, because it's much more efficient typically than writing things out. So writing modulus of an minus l is strictly less than epsilon is nicer than saying minus epsilon is less than an minus l is less than epsilon, or even l minus epsilon is less than an is less than l plus epsilon. Sometimes we will write it out using a pair of inequalities that way. Mostly it's nicer with the modulus signs, and the triangle inequality and all of those things will come into play. If you don't feel so comfortable with the modulus signs and inequalities, then I encourage you to make a conscious effort to try to practice using those so that you become comfortable with them too. So we've seen a definition of convergence. We've seen that we can prove that some sequences converge using this definition. It's not a super convenient definition to work with. So one key goal for the next video is going to be to prove a result that makes it easier to prove that some sequences converge. So a question for you to think about before the next video. Imagine we've got a real sequence an, so that 0 is strictly less than an is strictly less than 1 over n for all n. Does that tell us anything about whether the sequence an converges? What could you prove in that case? So have a think about that as a warm-up, and I'll see you for the next video soon.